let's see. Well, there's also average pooling that you'll sometimes see, and you'll just take the average of these values. But when you see pooling, maximum pooling is the most common. Right. So this is just to say something about the like the math, like we've seen a couple of times, like how do you take the current dimensions of your feature map, and then think about like the size of the pool and the stride that you use, and like and compute what the outcome is. Notice that that should be happening channel-wise. I didn't mention that. Should have. I showed you kind of like one channel. This is happening at every channel. Right? So at every channel you're replacing in that pool with the maximum within that channel. So while like in this case, while the output of the feature map is reduced, like the spatial dimensions are reduced by a factor of 2, the number of channels remains the same. And again, remember, think about channels as like your features. Don't think about the individual pixels within each channel as like the features. Think about the whole channel, the whole slice there as the feature. Yep, so common settings here, like I don't think I see much. Sometimes like a lot of networks don't even have the pooling in it anymore, to be honest, but they just use stride 2 convolutions to reduce the spatial extent. But when you do see this, the most typical is to do this 2 by 2 with stride 2. So just have these non-overlapping pools, and you use max pooling to replace the maximum value. Yeah, and then you do fully connected layers. And the way that you do that, by the time you get down to, by the time you go from here to here, you typically, depending on the network, but you've gone from something in the hundreds of pixels to something in maybe like the dozens or even single-digit pixels. And you can either like just flatten that all out, kind of like how we've done with examples, or you can do things like what are known as global pooling, which just considers the whole channel as like one pool, and you might average over all that, or you can take the max, something like that. But like in the homework, we're just going to stretch these out. We just flatten them all out, and you get one big long vector, and that goes into your fully connected layer. We're not going to do this because of time, but if you want to go look through there's just links to a nice video, illustrating these points. Okay, so just in quick summary, a typical kind of architecture for convolutional networks is to have linear convolutional layers followed by nonlinear activation layers, a couple of those kinds of things. That's kind of shown here. Then some pooling, and then finally finishing up with some fully connected layers that would go into something like a softmax layer to allow you to do classification loss through binary or through cross entropy, like multi-class cross entropy. What's trying to be shown here is a little bit of a regex here, just random expression for do this many times, convolution ReLU, then every once in a while do a pool, do that, do it n times in a pool, do all this m times, then do some fully connected layers, followed by again linear activations like ReLU, and then finally to softmax if you're doing classification. And you'll see it when we start going through like actual architectures. Many of the earlier architectures look like this. However, more recent and better performing networks like ResNet and DenseNet, we'll cover these. While there is some notion of this kind of architecture, like this kind of setting of the layers, they have additional connections between like layers, as you'll see, that it doesn't follow this kind of simple pattern, and makes them better than this for a variety of reasons, and we'll talk about those when we get there. Okay, so that's the end. So I'll switch over now to our next the next set of slides here. And today we're gonna talk about optimization. So far I should have stopped in there. Was there any questions? Sorry, plowing through here. Any questions on the end of that? What pooling is? There's your basic introduction. Yeah, go ahead.
So I guess I maybe you haven't like given this intuition yet, but it's not clear to me like when you decide like, oh, I'm pooling or
Right.
oh, I want to throw it away here or
Yeah. I mean, there's really no like a priori right answer, right? You know, like the basic thing we're trying to do is have a very nonlinear, family of functions, right? So when I say family of functions, it just means that there's like all these parameters in these networks, and you know, for each configuration of the parameters, you're getting a different nonlinear function, and we make nonlinearity out of alternating between linear operations like the fully connected layer or the convolutional layer, and then following that up with a nonlinear activation. So like those are kind of like basic principles, basic kind of building blocks, and we kind of just repeat that, right? Pooling was thrown in there because you know there was a need to reduce the size of the tensor maps or the tensors, the feature maps. So I mean, you know, why pooling? Why not something else? Why not do like a convolution stride 2? Well, like more modern networks actually just use the convolution stride 2 to do that reduction. Like why? You know, as opposed to pooling. Typically, the answer to why is, you know, there's either some computational reason, like this was faster, this was easier to, you know, like we got like the same behavior, or typically it's like we got better results by doing this. I mean, all of deep learning is really like empirically driven, right? It's really like what gives me the best results. There's really not a whole lot of like theory that you can go look at and say, oh, well, I'm solving this problem, so I guess I need 27 layers, you know, arranged in this way, and that will be like the best way. It isn't. It's really more like, in general, like, you know, what are like the families of functions that, you know, families of these neural networks that represent a whole bunch of possible functions and that like have good learning capabilities. You know, like in general have good learning performance. That's what you're looking for. And like things like ResNet, for instance, come about by a need to, by a desire to have much deeper networks than you were getting with this like a pattern that I just showed you. And again, it's just all empirical. I mean, I should say it differently. Like the thing that you do in ResNet that's different from what I just showed you, you know, makes sense for the problem that you're trying to solve. But like again, how many, like, why do that operation rather than like a number of other things that would be like it? Why make ResNets the way they are? It's just you try it, it works. You know, you have these like, I mean, there's a lot of criticism of this these days if you read about, you know, just reading kind of typical stuff on deep learning. But you know, there's been these data sets like ImageNet. There have been these benchmarks like the classification performance on ImageNet that have been used for, you know, a decade basically to make progress in this area. And there's been a lot of good, but there's been also like a lot of criticism about that. Same thing for like language data sets and the biases in them. It's all empirical in the end. One day maybe somebody will show us like the unifying theory of neural networks, but maybe it's what they're doing here. But you know, right now we don't have it. Good question. Okay, so far what we've learned to do is stochastic gradient descent, or vanilla stochastic gradient descent, right? Plain vanilla. So whenever you hear that, it's like, you know, like a simple basic version, right? And you know, here is a somewhat silly implementation of this, right? You have your way of evaluating gradients given whatever your loss function is, whatever your data set is, and whatever, you know, the current set of weights are. And with that gradient, you know, you descend it, so you walk in the opposite direction of which it's pointing. So that's why there's a negative sign. This is a plus equals operation, which just means it's really weights equals weights, you know, plus this whole thing, where it really is minus this. And you pick some kind of step size known as the learning rate, at which, you know, you're taking that much of a step in that direction. Okay, this is the basic thing. You know, you kind of, this is showing you like a little bit like a heat map. And we're trying to like descend into that minimum. You know, the way we set the problems up is at the loss, we want to go to minimum loss. So we're somewhere on the loss surface, and we're using gradient descent to get us to some local minimum. And we hope that's a good one. Okay, so plain vanilla stochastic gradient descent is kind of problematic. It's not like horrible, but it can have like really bad behaviors. Or it can just have like, you know, behaviors that are fairly easy to optimize. So that's what we're going to be talking about real quick. And what are the current, like, you know, things that, you know, solutions to those problems. So one question to ask here is, you know, here we are, we're trying to get to this minimum here. What if we have a surface like this? Like, so this is a surface. This is a two-dimensional. There's two, you know, your 2D parameters. Your surface is the third dimension, right? This is, you know, it's hard to see, but think this is like a bowl, right? And what if we're using stochastic gradient descent, and in one direction you have very rapid descent. That's what's kind of that's being shown by these contour lines being really close to each other here. And in the other direction, the descent is much more gradual, as noted by like the space between these contour lines. So what does gradient descent look like in this case?
It points you more in the direction of the one that's like the part of the gradient that's biggest.
Yes, and which?
Opposite direction.
Yeah, so like, yeah, so in this, the gradient you would compute here, you know, yeah, which direction would be biggest? This direction is vertical direction, or this horizontal direction?
Vertical.
Yeah, vertical, because it's the steepest, right? So that's right. What you would, yeah, sorry, I should have said something about here. Like if you know something about numerical methods, the eigenvalues or equivalently the singular values of your Hessian matrix, so like the curvature matrix, you have a really high condition number, meaning that like the ratio of one eigenvalue pointing in, you know, one direction in like a steep direction, and the smallest one, 2D, you only have two anyways, but in the other direction, they're very different from each other. That ratio is quite large. So when you have a large condition number, if you know anything about numerical computation, numerical methods, that's usually a bad situation. You usually get really unstable behavior. And that's kind of what we're trying to show here, is that what you're going to spend a lot of time doing when you descend like this is, you know, it really depends on your step size, but, you know, you're going to do a lot more movement in like this vertical direction than you are in this horizontal direction. Just because your gradient is pointing more steeply, there's a greater rate of change in that direction. And so you gotta, you know, because you don't really know what the step size ought to be, you know, a priori. This is kind of a difficult thing unless you start calculating things like the Hessian second order approximations to your function third order and things like that. That because you don't really know anything about that, it's hard, you know, you have a hard time picking that. So you're likely to maybe either overstep and do this kind of really wild zigzag thing, or have it really small, and yeah, you'll actually approach it more like this, but it'll take you forever. Like it'll take you, you know, computationally it'll take you tons of time because you're making very small steps.
So you talked about like using the higher order ones. Why don't you just remember the last gradient when you do stochastic gradient descent and just have that build up?
Why don't you use the last gradient?
Like remember the previous gradient of the previous step. And
yeah, that's actually like the very next thing we're going to talk about is the solution to this. So either you're a genius, which I believe, or you're ahead, or you just like you have a good feeling here. Like that's exactly right.
That's just like a really cheap way to get the second.
It is really cheap. Yeah, you're exactly right. Good job. So that's one of the problems. Another problem here is, you know, we're searching for local minima, but what happens if we get to something like a saddle point or very close to a saddle point? Saddle point being not a minimum, not a maximum, but, you know, in some directions, you know, the surface is sloping down, but in other directions it's sloping up. but center point being gradient 0 there. So what happens when we get what happens in gradient descent if we're near something like that?
Get stuck in the saddle.
You could get stuck in the saddle depending on the loss function, or of course, or on your step size, or of course you could jump right over it. But yeah, if you're using small step sizes, you're probably gonna, you're likely to end up kind of in it. And the trouble is it's been more or less kind of shown that there's a lot of, let's see if I say, yeah, there's actually a lot of saddle points. They're very common in these high dimensional loss functions. Something due to the symmetry. There's a paper here you can take a look at. Anyways, yeah. So gradient descent doesn't really. I mean, it's not like it's trying to get stuck in saddle points, but it's also doesn't have anything in it that's going to help you avoid them necessarily either. And maybe one more thing. This actually ends up being helpful in the end, but just don't forget this: is that when you're computing gradients in stochastic gradient descent, they come from these mini branches, these these subsets of your data that you're randomly sampling, and you're using that small set of data to estimate the actual gradient, which is what you would calculate on all the data. You're doing it again for computational efficiency. So what you're getting is it's a noisy estimate of the actual true direction of descent. Again, this actually ends up. There's a lot of work showing that this is actually beneficial. X is again a kind of regularization. That you take a little more of a random walk on the way down rather than just going straight down. And there's some interesting there's some cool papers that do things like oh shoot, what's the name of it? I'll think of it in a second and say it. But anyways, yeah, what's it called? Kolmogorov something. Gosh, I can't think of it. Too old. Sorry. But anyways, there's some some nice probabilistic dynamical system theory where you can kind of you can see the benefits of regularization. But nevertheless, you're taking an estimate here. So what do we do about all this? Well, we do. Exactly. Send me name again. I forgot it.
You took the previous.
No, tell me name again.
Anthony.
Yeah, Anthony. Anthony got this. So you do a thing that's known as momentum, and so in standard stochastic gradient descent, it looks like this, right? Wherever you are, you compute a gradient. You have a step size. You walk down it, right? You subtract that from where you currently are. And that gives you the next point in your iteration. By adding momentum, you do the following. You're actually keeping track of two things, both, x here is w, right? You're keeping track of the weights, but you're also keeping track of the gradients. And the typical approach here is to do something similar to what Anthony said, but to keep a kind of exponential moving average. So the way that that's implemented is you pick some value rho, which is this kind of this kind of momentum parameter. That's between 0 and 1. And what you do is the gradient or the direction in which we're going to do descent is not just the gradient, but you add to that this kind of this buildup of the history or this memory of previous gradients. But you're discounting that each time by this factor rho. So eventually, if you expand this, I think actually hopefully it has in the slide. If you think about that, doing this, rho your first estimate, the first gradient, as you build this up, it's gonna have powers of rho. And if rho is less than 1, then as you power that up, right, that becomes smaller and smaller and smaller. So over time, depending on the value of rho and how many iterations, the contribution of that initial gradient is going to go away. And this is mostly dominated by the current gradient, and then like the, some number of previous gradients that are being kept in this value b. And so you again step in that direction. And here's some pseudocode for that. But it's it's basically keeping the history of your previous gradients biased towards the most recent ones. So why is that any good? Anthony was kind of giving some answers on that. You want to
when you're going down the saddle, you'll just swash back on the other side, but then the one with the little gradient is going to build up and really take you down to the other side.
Yep, right. Yeah, so, instead of having it, if you think about that example of going back and forth, back and forth, back and forth, if your first gradient kind of pointing you this way, the next gradient wants to point you, back the other direction, right? But if you keep around a small portion of this, and then you add those together with the current gradient, then when you add those two things together, you get something that's still pointed like in the direction of the gradient, but it's not this wild swing, right? Because it's still got some history of what it's done previously. And then once you do that a couple more times, you get this far smoother approach to the to your minimum than you would have had it without that. And that's basically what it is. Yeah.
So when you visualize the loss surface, and there's a lot of local minimas, how often would you see a saddle point versus the regular minima?
It's impossible to say for any one problem. There are great papers on this where they took very easy to understand, loss surfaces and did that kind of stuff.
If you have at least just 3 local minimas, you should have at least 1 or 2 saddle points, right?
No, you don't necessarily have to have that. You don't have any saddle points. But just when you get in the higher dimensions, it becomes more. It becomes high. There's a higher likelihood of that, coupled with the kinds of functions that we are able to estimate with our neural networks. Yeah.
So the intuition behind this method is that the new gradient doesn't deviate much from the old gradient, right? Because we're adding the old gradient.
Well, yeah. It just means that it just means that the current gradient has got some discounted history of previous gradients in it. You can still get kind of wild behavior there depending on the loss surface, but in general, it really smooths out your learning dynamics. And let me just say that stochastic gradient descent plus momentum is one of the most commonly used optimization schemes in deep learning. We're going to get to another one here soon that is also common, but you rarely ever see SGD. In fact, this is usually a really bad idea just to do plain vanilla stochastic gradient descent. If people tell you they're doing stochastic gradient descent, they're almost always doing it with momentum, and they just aren't saying it because it's just so common. Go ahead.
Yeah. So how many class gradients do you look at? Is it all or is it after?
Well, it's all. Remember, it's all because of this recursive formula, right? Because it's V2. So start with V1 or V0, right? So V1 has got V0, which is just the gradient. Okay. Then V2 has V1 in it, which has the original gradient plus the next gradient. Then V3 has V2 in it, which has got the first 2 gradients, and then the third gradient. What's happening though each time when you multiply all of this by rho is that it's not really just with that gradient in it, but it's with some power. It's that gradient with some power of rho, right? So every time you take a step here, you're discounting this by rho. So the first gradient, if you take an n, if you've done n iterations here, it's going to be rho to the n minus 1, I guess, and for that first gradient. So remember, rho is between 0 and 1. That's getting really small. So the contribution of the first gradient to this portion, of the momentum term, is going to be small, and it's going to go to 0 eventually, just depending on how many iterations that you've done and what the value of rho is. If rho is very close to 1, it's going to take a long time to remove that memory, but if it's much smaller, it's going to go away really quickly. So that the rho is a kind of hyperparameter for the dynamics of learning here. Does that make sense? You just kind of write it out one time for yourself. You'll see it. Yeah.
So is it possible to measure the gradient of gradient so we can identify saddle point or
Yeah, so you're saying, could you do like a second order thing where you actually compute the Hessian, where you have the full matrix and the curvature? You can do that. Look, that's going to be one of the things that we look at here at the end of the lecture. We'll talk about some second order methods, but you don't typically see them again because your computation, like you square the amount of computation in that case, right? You have to, instead of n entries, n gradients, or n partial derivatives to take, you now have basically n squared of those, and that's typically bad, right? I mean, sometimes you might want that, but you very rarely see second order methods being used here. Again, because they're just so inefficient. It's just better to do these plus other tricks, and these tend to converge really well, much faster in the second order, and you get to a similarly high quality local minimum. Good questions. Just like a different implementation of where you might,
that's easier to understand.
Yeah, maybe. I mean, in the end, it becomes the same thing because there's this alpha, it's always here and factors out. But anyways, yeah, this is the equivalent implementation. Okay, so how does this help, right? So we talked about it. Going back to that, instead of going back and forth, depending on the choices you make, you'll much more smoothly approach the minimum. What about for saddle points? How does this help?
It ensures that gradient is never 0.
Right. So like, if you're really close to a saddle point, right? It's like you had to approach it. So you have some gradient information, built up in the history to get you close to the saddle point. But if you're close, you're going to have a small gradient, which makes it so you wouldn't move. But if you have this momentum term, you have this history of your gradient, then that's going to help you to move right past it. In the same way, it's actually going to help you it could actually help you, depending on the step size you take, it could help you to move right out of, a local minimum, like that basin as well. So there's a balance that has to be done here. And it's a little bit of a delicate thing, and there's like complicated things like learning rate schedules that actually change the learning rate as the number of iterations increases, things like that. And we'll talk more about that. But in general, this helps to solve that problem. Okay, so that's not the end of it. So stochastic gradient descent plus momentum, very common optimization scheme. Okay, in fact, so common that again, like if you're talking to somebody about stochastic gradient descent, you're talking to somebody who does neural networks for a living, I guess, and they talk about SGD, they're almost certainly talking about SGD plus momentum. They just go together. Okay, what other approaches could there be here? So there's a different take on momentum called Nesterov momentum. And Nesterov momentum, so with momentum, you'll have your gradient, you'll have your velocity vector. So this is the current gradient. This is like that historical momentum term, and then you're going to add those two together, and that's going to be your these two vectors add together. This is going to be your actual step that you take. For Nesterov momentum, what you actually do is you take the gradient at the point that that the velocity term, like that momentum term, would have put you to, and then add them together, and that is your step. And turns out that tends to have maybe somewhat better properties. If you've done any sort of like optimization, this is in the family of look ahead optimization. That's like where the thought is that really, like if you have a term like this, really this is no longer the local gradient you want to compute. You really want to compute a gradient, here like ahead, looking ahead. And so there's, like if we do some of the theory like this has this kind of optimization has a better, like as a more well-behaved, like things like the condition numbers and things like that become more well-behaved, become bounded in certain ways. Nothing that we're going to get into in this course. Just know that this is a thing, and it looks like this. So, sort of taking that like second formula for the momentum term, everything looks really very much the same, but instead of computing the gradient here at x, or should be w, given what we've been using so far, you compute it at whatever this is plus the momentum term, and then that's your gradient. So it's very similar. You're computing your gradient at a different location, and then doing the update.
So why don't we look ahead one more time, and then we get a parabola, and then we can just find the minimal of that parabola.
What do you mean by look ahead one more time? Because
so if you have 3 points, you can fit a parabola, right? And then you can just find the minimal.
But you're proposing like adding like that to it again?
Yeah.
Well, that would be collinear, so you wouldn't have a parabola, right? You're just going to keep stepping in the same direction. Like you can't look ahead another time. You have to do the operation to get you to a new place, and then only one look ahead here.
Can we just look back then, and then see?
You could do. I guess to the forward or the back. I don't know. Yeah, there's a great like end of the semester project. Like maybe that's a brilliant. I mean, maybe I don't know if there's work in it or not, but maybe that's a brilliant new scheme. But yeah, so this is known as Nestorov momentum. Don't get it confused with like plain old momentum. It's this look ahead momentum. Yeah, like I do some sort of change of variables, and you can see a little bit more of like a look ahead operation here, like when we do this update. What you really have is this discounted term, like the difference between those past two gradients. Yeah, that's the thing. Okay, there's some pseudocode for it. Cool. All right. So there's your kind of momentum. Like the standard kinds of optimization schemes you can see that involve just momentum. Okay, so now we're going to move on to the next set of optimization schemes, and these are these all kind of come with a name. Not all of them, but like a lot of them come with a name. There's a whole bunch of these in this family. We're just going to go through a couple of like the more popular ones, but they have like an ADA something in them. And the ADA stands for adaptive, and of course grad there is gradient. So ADA grad, not very commonly used, but was kind of like the first in this family of optimization schemes. And what is it doing? Well, it not only So what does this one do differently? This one actually keeps it around a momentum of not the gradients, but the square of the gradients. And then what do you do with that square of the gradients? You divide by the square root. So by the square root here kind of brings, if these had units, it brings the units back to like the correct set of units. But importantly, you're dividing by some some positive term here, or it should be positive. Some positive term here. So instead of no momentum like in the way that we just described. Although very quickly we're going to put them all together, as you might anticipate. But we're subtracting off our typical stochastic gradient descent update, right? So learning rate times the gradient, but we're now dividing by the square root of squares here. Okay? And by the way, all these operations are being done element-wise. So this is not like the Hessian. This is not two partial derivatives. This is like the gradient entry-wise multiplication with itself. Okay, so you still have a vector. It's just like you just squared all the entries, basically. Okay?
So it's just going to decrease over time. The learning is just going to decrease a lot over time.
Okay, good. Yeah, that is one of the consequences. Actually, the question will come up here in a second. But yeah, let's just start to think about this for a second. So one thing that's put on here. So first of all, remember that there's still kind of this notion of like momentum in the sense that there's this plus equals here. So we keep adding these squared gradients here, and then we're taking the square root of all the all those squared values. So this was the comment that was just made by Anthony, which is like what's happening then to this denominator every time we do this.
Just kind of going down.
Yeah, this denominator just keeps getting larger.
Yeah.
We're dividing by it, so we keep dividing by every iteration. We divide by a larger and larger number. So if you think of this as being like adapting the learning rate here, then it's actually over time it's making that learning rate smaller and smaller and smaller. This actually is a somewhat, depends on how fast that happens, but it's somewhat desirable behavior. You typically want to start with large learning rates, do a lot of movement, kind of exploring your loss space, but then hoping that gets you into like good parts of your loss space. But then you want that learning rate to get smaller and smaller as you're like, getting into the basin of a minimum, and you're wanting to get really close to it. What you don't want to have happen is jumping over it, right? Which can happen with large learning rates. So this is actually making it smaller. Do you have something?
Yeah, if you actually hop over it, can't you just roll back down to?
Yeah, but then you didn't hop over it, right? You can hop into new areas of the loss function where the gradient step will take you some other direction.
So what's the difference between this method and just like manually decrease the learning rate over time? Just like that, like a schedule or something.
Yeah, that's a really good question. Let's answer that. We do that kind of scheduling, by the way. It's not like we do this and we don't do the other one. But this has some good properties. So let's think about that. So what happens to? So remember, this is all happening element-wise. So what happens to like the learning rate for like a dimension, the element, a dimension where the gradient is actually quite large? We're going to divide by something that is what? Large or smaller? Large, exactly. And if the gradient is actually quite small, yeah, this is the question you're asking right here. If the gradient is quite small, when we divide by it, what's happening to like the learning rate in that direction? So if the gradient is small in that direction, what's happening to the scaling that we're doing of this learning rate in that direction? It's increasing it relative to a large gradient. So it's adapting the learning rate. The way this is implemented, we're actually not changing anything about this. Just the thing that we're like dividing by here. If we have a lot of large gradients, then we're going to be dividing by a value that's large. And if we have a lot of small gradients, we're going to be dividing by a value that's small. So it's kind of introducing like something like a natural scale for each of the dimensions with respect to the gradient. That's kind of evening out the learning rate in each dimension. Is that making sense? I see some cases that are like, yeah, and I see some cases that are like, no. So be brave, yeah.
This is not making sense to me because we're squaring the gradient.
And then taking a square root.
Square rooting it. So doesn't that just give you the absolute value?
It would, except that you're actually doing this operation. You're adding
Oh.
You're adding these every time, so
I see.
eventually, eventually everything here is going to be large,
I see.
right? Making this small.
I missed the plus sign.
Yeah,
Thank you.
no worries.
Isn't that penalized if you have a big gradient in a certain direction, but like this is the direction you really want to be going?
Yeah, I mean, locally it's maybe the direction you really want to be going, but it may not be. You may not want to go that direction for very long, because this is a crazy loss area. They're not, we're showing these like really nice pictures, like these nice convex loss functions, but in general, these could be doing all kinds of wild, crazy things, right? So it's a somewhat natural way of adjusting the learning rate with information about the gradients that you've computed so far. Yeah, what happens to the step size over a long time? Sorry, I think I skipped over this. What happens to graph? Progress along steep directions is dampened, right, because you're dividing by something large. Progress along flat directions is accelerated because you're dividing by something small. And we're talking about like relative to the other directions, right? Like it's not absolute. Okay. And like we talked about, because of this plus sign, you're accumulating, more and more and more stuff in this denominator, and so eventually, the learning rates, the per dimension learning rates are going to zero. Okay, so there's some pseudocode, actual code for Adagrad. Now there is another very similarly related optimization scheme called rmspro that actually there was never a paper written about it. This right here is a reference to like a talk that was given where this was introduced. But nevertheless, like people, tried the thing that was in this talk, and it became, and it's like pretty good. It's actually used quite a lot in like NLP. If you've done any NLP already, you might have already used rmspro. And yeah, it's one of those other optimization schemes that you kind of see, like that are always implemented in things like TensorFlow and PyTorch and those kind of things. Like Adagrad, rmspro, the different stochastic gradient descent and the different momentums are always there. So this is very, very similar to what we had before, but there's some slight change. And what's the slight change?
Yeah, there's a decay.
Yeah, there's this parameter that's here called the decay rate. But notice how it's, decay rate times grad squared, so like whatever, like memory here. But we're adding to that 1 minus the decay rate in the current gradient squared. So like what's that doing? Yeah. Yeah, what you're trying to do, so here we had this whole thing about like you just keep adding more and more and more. This kind of thing right here is trying to say, well, you are doing lots of adding, but having this parameter decay rate between 0 and 1, you have some fraction of the current gradient, and then some fraction of the historical gradient, and you have some fraction of the current gradient. Those add to 1, so you're kind of getting like a balance here, so that instead of just like always adding more and more and more, you're more or less just kind of like you have something like on the order of the original size. Of course, it doesn't really work out that way exactly, but it does tend to preserve that, so that this denominator here, this denominator here doesn't get as huge as fast. It doesn't like damp out learning as quickly, right? So it's kind of more of a balance between that, and allows for learning for longer.
So you showed a picture earlier where like it was all stretched out in one direction. So when you do this, doesn't it just kind of make it more square?
It's something like that. Yeah, if you think about this as like a kind of change of a change of scale per dimension, it's like a way of kind of putting them all on some similar scale with respect to the gradients. It's not perfect, but that's the intuition for sure. Cool. And it's called rmspro. Any questions about that?
Which one's better?
Yeah, people rarely use AutoGrad. You do see rmspro. But the thing you see, oh, right, forgot. Ooh. So here's some, interesting loss surface. And what you're seeing are the learning trajectories for these different optimization schemes, except for we haven't learned to add a delta. But anyways, there you see like here's what SGD would do, here's what momentum would do, and so on and so forth. The Nesterov, momentum, AutoGrad, and rmspro. All using the same learning rate, like initial learning rate, and you get some sort of sense for like how these dynamics work.
What is NAG?
That's the Nesterov momentum.
Is there the A? Is that adaptive or?
No, that's I actually don't know why it says AG, to be honest. It's a Nesterov. I didn't think what it would be. I don't know. You can think of it. You can make it up. But it's just Nesterov. Cool. So I don't know. It's just one loss. It's just one loss surface. It's just one like initial point there. It's just one like learning rate. You change all those things, you're gonna get something different. But it kind of gives you some idea of like why like how these would behave, and looking at a loss surface, like why it might do that. So notice how. So in this case, in our heat map, it's kind of like it's actually like the colors are inverted. Blue is lower, where before like red was lower. But you can see what's happening with like the momentum terms, right? Right here, this is all pretty like flat in this direction, right? Because the contour lines are kind of spreading out. But we start here, so our initial gradient is actually quite large, right? They point in this direction. So these momentum optimization schemes, like remember that initial gradient and move it, because of that, for a long time it's actually moving us in that direction. When we start to kind of make some moves, and like Nesterov, as you can see, kind of more quickly moves you over in the direction of the actual minimum you're going towards. But they're moving in this direction because of the gradient there. And the point you're seeing with some of these used for AutoGrad and for rmspro and add a delta, which is doing something else, is that because it doesn't have that kind of momentum term, but it's balance, it's adapting the per dimension learning rates. It tends to more quickly move you in the right direction. And also just notice that like stochastic gradient descent is just kind of slowly making its way there. So you might think, well, stochastic gradient descent in this case is like way better than the momentum terms, because like these things have a trajectory that take you way away from where you want to go. But notice that in the end, they get you to where you want to go much, much faster. Again, because there's this kind of memory pushing you in certain directions.
In this case, is there a way to combine like adaptive, get everything in proportional first, and then do your momentum?
Yeah, more or less, and that's what's coming up next. So here's Adam, and this is, besides stochastic gradient descent with momentum, like the other most popular. This actually might be the most popular optimization scheme to use, especially like when you're first approaching a problem. It has like kind of all the things in it, plus some even smarter additional things in it as well. And this is not quite it, but this gives you like some idea of what's going on, and then there's actually some kind of there's There's a statistical kind of correction that happens in the actual atom. That's why it says atom almost. But what do you do here? So notice that there's going to be these like moments that we're going to memorize. These are like our momentum terms. There's the first one and the second one. So like all gradient descent methods, we're going to compute gradients. And then what do we do here? Well, we have these two terms that look like the RMS prop terms, right? For the what was it called in that sense? Or that in the RMS prop? Can't remember now. What is it called? Oh yeah, the gradient square. Yeah, that's what I couldn't remember. Okay, so just it looks like these, right? We're picking some parameter between 0 and 1. They're two different ones, and we sort of have this balance between like we're keeping a history of the gradient and then the gradient squared. So kind of like the momentum, kind of like what we just saw with the RMS prop. It's not quite the momentum because instead of what we're doing is we also have this 1 minus beta term here, which we didn't have with just like the straight up momentum. This is more like what we have from the RMS prop. This this kind of convex combination of these using these parameters gives you something that's kind of preserving like the overall scale of the gradients or the gradient squared. And then what we're doing is we're using this first momentum term, or moment term, like the momentum term in our momentum calculations. The gradient doesn't go here, but whatever we're tracking here. And then we're also dividing by the something related to the gradient squared. So it looks like a combination of those like two those two kinds of methods. So it's kind of like what you were getting at, right? It's like, can you combine these? Well, here's like the most straightforward way. Combine them almost. I guess it would be most straightforward if what they had done was to not have this term here, but it turns out that has some good benefits.
Was this really published in 2015? So this is only like 6 years ago?
Yeah, but it feels like millennia ago, right? For like 2 billion people. 2015 might as well be like
The Dark Ages?
it might as well be like the 1700s for physicists or something. I don't know. Like you just have Newtonian physics or something. I don't know. So yeah, kind of. I mean, again, just it kind of combines the two ideas, and you'd say, great, like let's leave it at that. That probably works great. And actually, it would work pretty well. But the people working on this noticed something about what happens like near the beginning when you start doing these iterations. Especially due to the fact that we are initializing our first and second moments as zeros. Okay? So let's see, do I have it? Yeah, okay. Sorry. Sort of like RMS prop with momentum, right? So what happens at this first time step? Well, the first and second momentum are 0, right? So what is our what's our first? What's the first moment? What's the second moment?
Just 1 minus dx.
Yeah, so it's like it should be just the gradient, right? Like if you're just starting this thing off, really it should just be the gradient. But you're dividing by this term here. So what happens is that like this adds a kind of bias to these like estimators, like these moment estimators here. Where it's called first moment because it's supposed to be estimating something like the first moment of this scheme, which would be like a first derivative. But you can already see that it's not, even in the early stages, it's not actually the correct derivative. It's you're multiplying by some constant. And it's the same thing too with the square of the gradients. So, and this kind of behavior persists again because of the zero initialization of the first and second moments. So what they did was to actually do a kind of correction that removes this bias and removes it for all time steps. And what they do is instead of actually know, what we had before, where this is at first moment, and that's at second moment, there's this term called first, you know, like you unbias it and second unbias it. What they're doing is they're just taking these moments and they're dividing by 1 minus beta 1 in the first moment case and 1 minus beta 2 in the second case, but to the power of t, or the number of times that, the number of iterations that we're doing here. So in the first iteration, what happens? You know, this first moment is 0, so this term goes away. And you have 1 minus beta times the gradient. If we divide by this, where in the first iteration t is 1, we're divided by 1 minus beta 1, and we just get the gradient in that first step for the first moment. And similarly for the second moment, we're just going to get the element y square of the gradients there when you divide by this. And so, like in that, you know, in that first operation, like you're getting exactly what you would have expected. So why to the t for the other iterations? Well, in the paper, you know, there's a bunch of math to show that, like, actually, if you do divide in this way, what you get is an estimator that converges on iterations to the correct, unbiased moments of this optimization, of an optimization scheme of this order. And anyways, it's a bunch of math to justify this. And so this is what's used here. And what is this doing, right? What's happening here? As t goes to, as the number of iterations becomes large, I didn't say this before, I guess, but it's not up here, but again, the beta 1, beta 2, they're between 0 and 1. So what's happening as you sort of increase the exponent on beta 1 or beta 2?
Large, or it gets really small.
It gets really small, right? So like the thing that you're dividing by here actually goes to 1. So what this is really just a correction for the huge amount of bias that you add into this scheme at the early parts of the for the early iterations, but then kind of later on it kind of washes itself out, and then you can show that the expected behavior here is to get the gradients and the square of the gradients. Anyways, so this is what's called atom. You have like the momentum-like term. You have the like atom-grad, or really the rmspro type term, and then you have this kind of statistical correction, so that even like at the beginning of the early iterations, you get good behavior, and as a result, this becomes a really popular optimization scheme. It's used all the time. If you start reading papers, you'll just see that most of the time it'll say, we use this network, blah 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 blah. We trained it using atom. Almost always these beta 1, beta 2 are chosen in this way. It's almost always, it's like always the default. So like when you go look at your PyTorch implementation, your TensorFlow implementation, rarely do people change it. It's just like, you can use, it's really robust to different kinds of learning rates actually because of the adaptation that's done here. Like you could choose a lot of different learning rates, and they all basically kind of learn the same. It ends up being really nice. Interestingly, yeah. How much time do I have? Yeah, 10 minutes is good, right? Interestingly, it turns out that like usually you can do best with stochastic gradient descent plus momentum. Almost always you can get your best performance with that. But that takes a lot of tuning, and so usually people start with atom to get themselves into a place that like looks good, and then if they really want to, they'll make a change from there and then start using stochastic gradient descent plus momentum and like find a more optimal solution, set of parameters. But anyways, now if you weren't already overwhelmed by all the choices you have to make when doing neural networks, now I've given you another one. You have to make all these choices about which optimization scheme to use. So like, which ones do you use? Or like, which learning rate do you use? That's also another, parameter that you have to choose. there's a lot of choices here, right? And what this is trying to illustrate is that like usually if you choose like a really high learning rate, you're just jumping over everything. Doesn't necessarily mean that you go find like the highest loss ever, but like usually you're not going to converge to anything. You're just going to have to stay at the random loss level. So that's just because like you're not learning anything. You're just kind of like stepping around in this loss function, finding all kinds of crazy places. Low learning rates will get you to some minimum, but it may not be the best minimum because you didn't really explore the space. Like you're starting off kind of near a minimum, and you like just kind of walk into it, and it usually takes forever because like you really only want to take small steps when you're like in the basin of the minimum. You want to take big steps when you're further away from it. So this usually takes forever. Like there's some good learning rate in there where you have like good trajectory of like reducing this loss over the number of epochs, and finding a really good minimum where you're getting that loss down quite low. So how do you decide which one to use? No one knows actually. There's like again for most problems, there's not like a priori like here's like the optimal way you'll do this. However, what people do is they use what are called learning rate schedules, and these learning rate schedules will typically have a learning rate decay over time. So you can start large, but after a while, you have some way of decaying. So like there's like a typical thing. Step decay. Do I have a picture of it? Yeah, so like this is what step decay would look like, right? So it's like I have some sort of learning rate, and I kind of reduce my loss, and I'm here. Then I maybe like divide by 10, and I reduce again because like I'm able to kind of get into a basin of a minimum or like into a place where I'm not taking steps over this. And then after a while, it starts to plateau. I do it again. Now I'm able to get even closer to the minimum. This is like a really common learning rate schedule, and it depends usually on like the the gradient of the loss. So like as that starts to plateau, it's like an indication that you want to reduce the learning rate again, so you can take smaller steps. But there's other ones that people use, not very often. Usually you don't see these actually, but they're implemented in most frameworks like PyTorch or TensorFlow. Exponential decay, right? So you start with some initial learning rate, and it just some very small k over time. This is just going to keep reducing it. Same thing here, just the k kind of determines the rate at which you reduce the learning rate. But the t there is like every mini batch, right? Every time you're taking a step. So like the reason again for doing this is that it doesn't, instead of having the burden on you of like figuring out what's the exact right learning rate, you can typically find an initial learning rate in an appropriate range, and then use one of these to kind of change it over time in a reasonable way, so that you get some good dynamics. There are other ones here that aren't in these slides that I should really add a slide for. There are interesting learning rate schedules, like they're called like cosine schedules, which so there's usually a warm up. I guess that's why we don't talk about these. But you reduce. It's like there's a lot of ways of doing this, but you like increase for a little while, and then you decrease, and then you follow more like the way that like cosine would approach 0 rather than like an exponential or something like that. That's a very typical one. You'll see these in the frameworks as you start using them. Question.
So among those three, which one is the best practice?
Usually, the one that you see is either this one or like other ones that are becoming really popular right now due to like demonstrations of their abilities on things like Kaggle and stuff, like cosine schedules. But usually you'll see like a step decay. You won't really see exponential. Exponential actually has pretty bad properties, as some papers have shown. But importantly, you typically only use these things with like SGD or SGD plus momentum. You know, atom or the adaptive learning rates you typically don't need to do those because they're already kind of adapting, you know, the learning rate perfectly given the gradient information. But there's nothing stopping you from doing it. It's just that you don't you don't have to. You don't gain some benefit.
Is there any point to like trying to get this just perfect, or
not usually.
like if you get like, because what are we fighting for? Are we fighting for like a 1% more or a 10%?
Yeah, right. It kind of depends on. I mean, it depends how good or bad you are at doing this, right? So like if you're pretty good at this, you can pretty quickly get yourself into a place where, you know, like you have really good performance, and now like eking out additional performance is going to be it's going to be very costly, lots of experiments for not much gain. But if you're really bad at this, then yeah, like exploring actually will help you and help you get good at it. All right, so in the 2 minutes that we have, I just want to make this mention of this second order optimization. So what we've been doing so far is first order optimization, right? Wherever we are, compute a gradient, we take a step in that direction. What you could be doing is doing second order optimization where you actually use the gradient and Hessian information to form not a linear approximation at that part of the loss surface, but a quadratic one. So you have some notion of the curvature, and this will almost surely, you know, allow you to get to minimum quicker, because again, the curvature is like you're trying to approximate this in some way with the square of the gradients, but of course it's not actual quadratic behavior, curvature behavior, but here you're actually getting real curvature behavior. So you not only do you know like the direction of steepest descent, but you also know that as you move away from this, like what kind of curvature to expect. You know, it's like how rapidly does that like change? You know, that best direction change, and that allows you to set a kind of natural scale for the step sizes. And this is just related to like Taylor expansions. If you've done this, you should have done this in calculus classes, or you use this in applied math or whatever. But again, the important part of this is that it gives you a natural way of it gives you natural learn rate, so to speak. This is bad though for exactly the reason that we talked about. Computing a Hessian, you know, if you've got n dimensions, you have to compute n squared partial derivatives. Not only that, you're going to have to, if you want to solve this here, solve this for the updated parameters, you're actually going to have to invert that Hessian, which now takes, which has order n to the n cubed operation. So, you know, this is bad. Sorry, I said dimensions. I didn't mean dimensions. Remember, these are the weights, right? So if you have like a huge network, this computationally, this is ugly. There are some approaches to this that people have proposed and used successfully in some problems. So quasi-Newton methods. So, right, all of these are ways of approximating the inversion operation of that Hessian matrix. So BFGS, named after these swell gentlemen, is a way of approximating this, but with rank 1 updates. So this is like a rank 1 matrix is pretty easy to compute. It's the outer product of a vector with itself. And then there's a version of this that limits the memory consumption, where you actually don't form the entire Hessian. But the truth is that you never see these because they're still very expensive to compute. And with all the modern tricks that people use, you can usually do just as well or better. And yeah, a really good point here is that these don't transfer well when using mini batch. So like all that noise that's added to a mini batch, like so like the noise in the gradient, that noise becomes quadratic in the Hessian, and that becomes a real problem. Like you have really, really bad estimates. So again, in practice, people use atom. That's almost always like a starting point, and then when they really want more performance, you might go to stochastic gradient descent plus momentum. You're just going to take some time to tune it. Okay, that's it. Thanks, everybody.